Talking about area and distances. We're in chapter 5 now, section 1. So the objective here is to determine the approximate area under the curve and find the distance traveled by an object traveling at a varying speed. So first, as a warm-up, we're going to do the area problem. We know how to calculate the area of certain shapes, such as this. We know it's a rectangle, so we know that the area is, in fact, base times height. And we know the area of a trapezoid is base 1 plus base 2 over 2, and that would be times the height. So really just the average of the bases, where you have base 1 on the top, base 2 on the bottom, and then the height would, of course, be the perpendicular height. And then here, we'll just label this as base and height here, and the area, I'm using the disappearing pen, so I'm going to have to go back and fill that back in. So I get area is base times height, and then area is base 1 plus base 2 over 2 times the height. Funny, funny teacher. All right, so now if we're dealing with area of these rectangle and the trapezoid, the rectangle and the trapezoid, we have units of miles per hour for the height and 5 hours for the base. So if we label them 5 hours and 65 miles per hour. And then over here, we'll label it base 1, base 2. And you might think this is the base, but it's not the base, because in a trapezoid, recall that the bases are the parallel sides. So we could say base 1 and then base 2. And base 1 is given and base 2 is given. And here is the height. The height would be the perpendicular height from the parallel sides. So for the area for the first one, we should work this out. And if you want to pause your video at this time, it would be 325 miles. And you wonder, isn't that miles squared? No, because you're multiplying miles per hour times hour, which turns out to be miles. And then for the second one, pause your video and find the area. And then now you're back on again, and this is 50 meters. Okay, so we're not used to having units of area to be linear, what seems to us to be linear, but that in fact is the units when we use the area as a modeling. Then, considering the polygons below, we can find the area by dividing the polygon into triangles. So if you take a look at the first one, you can definitely see it's divided by triangles. The Greeks use this method called exhaustion, and you can imagine that they would get really exhausted if they split up, say, a circle into maybe how many triangles? 2 million triangles, right? That would be exhausting. So the method is called exhaustion because of that. You kind of exhaust the efforts until you can't go any further. So if we consider this shape, you have 6 sides. So we know that as a hexagon. Thank you, Tori. A1, A2, A3, A4 for the different areas. Now let's use a little summation notation for this. This would be representative of the summation from I is equal to 1, and since there are 4 sub-areas here, 1 to 4 of A sub I. So all this would mean is that we would take A1 plus A2 plus A3 plus A4. So if we took a polygon, a hexagon, and split it up, we could definitely find the area of those 4 triangles. Well, the Greeks did this with circles. They took the number of sides of a circle to infinity, where you have A6, the area with 6 sides, the area with 7 sides. So a 6-sided polygon on the inside is called a hexagon. What's a 7-sided polygon called? A heptagon. And then a 12-sided polygon is called a dodecagon. Yes. The Greeks took this as the area of a circle is equal to the limit as the number of sides and the number of sides approaches infinity of that A sub n idea that you see above. So they were able to approximate the area of a circle, and you know today it's pi r squared. Got to clear this off. Edit, clear ink from the page. That's where we ended yesterday. Okay, 5.1. We will approximate the area under the curve and also interpret it when the dimensions are velocity and time. First, we examine f of x is equal to x squared in this context. So we're going to use rectangles to estimate the area under the curve of the parabola x squared. Here's x squared. So x squared is the curve as you see it coming up. And we're using 4 rectangles from 0 to 1. So we have 4 rectangles of equal length. So in this, we want to say that if we find the area total, it would equal to the summation from I is equal to 1 to 4 of all the a sub i's. And without getting too deliberate about this, we're just going to say it's a1 plus a2 plus a3 plus a4. When I say deliberate, we're not going to get into the calculus rigor yet. So we're going to calculate the area of each one of these rectangles by using the base and the height. So if we look at the base of each rectangle, you can clearly see that it's 1/4. The delta x at the base is equal to 1/4 as we go upon the intervals. So that means to get the area, it will be equal to, so I'm going to say a total, I'll put t here, is equal to, consider what is 1/4 squared. Then at that point, I'm going to put the height of the rectangle right above the rectangle. It would be 1/16. Because our function is x squared, it would be 1/4 squared. So the second rectangle would be 1/2 squared, or 1/4. The third rectangle's height would be 3/4 squared, which would be 9/16. The fourth rectangle would be 1 squared, which would be a height of 1. So on top of the rectangles, I'm just noting their function values for the point on the right-hand side. So we get an area total, which is equal to, we'll take the first rectangle would be an area of 1/4 times 1/16. Then for the second area, it would be 1/4 times 1/4. Plus the third area would be 1/4 times 9/16. Plus the last area would be 1/4 times 1. So if we combine all these, we get the area that is approximately, we should get 15 over 32. 15 over 32 and this would be then, if you consider for a second, it's an overestimate because the rectangles are above the curve. This is an overestimate for the area. Taking your graphing calculators and putting y squared into your graphing calculators. Let's do that quickly. Y equal, and clear it. We'll put in x squared, x squared. Now we're going to find the actual area, and then we'll be comparing it to the next 2 examples as well. So if we hit second trace, and 7 for the area function, the antiderivative, 7, and we'll talk more about that, but just using 7 right now, and it asks you for the lower limit. The lower limit would be the lowest x value under the graph. It would be 0. The highest limit would be 1, or the upper limit. So we would get the area as 0.33, or 1/3. So the actual area, just to note the actual area, the actual area is equal to 1/3 if you consider only that area that's underneath the curve. Okay, let's try the left endpoints then. Using left endpoints on the rectangles, estimating the area. Using the left endpoints, you can see the first rectangle doesn't exist. There is no area, but we'll talk about its function value as well. So now you know that in this case, what's delta x equal to? That's right, it's 1/8. So now as you go across, putting the function values right above the rectangles, the first one is 0. The second one is, well, it's hard to see, right? So you've got to get this idea of what are the function values. So when I handle this one, I'm going to look at the fact that I'm looking at L, and yet there are 8 subintervals, so I'm going to call it L sub 8 is equal to. I'm going to do the function notation here because I need the function value. And remember that at the end, what we could have done above is we could have factored out this 1/4 because the 1/4 is a factor in each of the products for area. So I very well could have put it right out at the end using the distributive property, and that's what I'll do with this one. What we're going to do is take f of, I need the value. So what I would do is use 1/8 as a counter, 2/8, 3/8, 4/8, 5/8, 6/8. And when they can simplify, then of course do that. So the first function value would be f of 1/8 plus, then we have f of 2/8, which is f of 1/4 plus, then we have f of 3/8 plus f of 4/8, which is 4/8, which is 1/2, plus f of 5/8, plus f of 6/8, plus f of 7/8. Okay, now, are we done yet? Do we use the 1? No, because here's 7/8 right here. This is where we stop for the function value. We don't use that endpoint, so only these endpoints, left endpoints. So let me just put this. Now, do you notice I left out f of 0? I probably should have put that in there. I'm going to put it in on the end, but just to be correct here, f of 0, because that is the first left endpoint. So, and then I'm going to multiply this times delta x, which is 1/8. Okay, so now with these, we just have a little bit of figuring to do. But remember, all you're doing is squaring the x value. So what do we get? We get f of 1/8. So L sub 8 is equal to 1/64 plus 1/4 squared, 1/16, plus 3/8 squared, 9/64, plus 1/2 squared is 1/4, plus 5/8 squared is 25/64, plus 6/8 squared would be 36. It could have been, what should we say instead? 3/4. I'm sorry, I didn't write that here, but 3/4, and that would be 9/16. Plus, then we have 7/8 squared, which is 49. Put that over here, 49, I'm going to just write over the line, 49/64. And then plus the 0, okay? And that would all be times 1/8. So parentheses around the whole expression from beginning to end, and then multiply it times 1/8. And you should get a value of 35 over 128, which is approximately 0.27, I think. 0.27 something. 3 digits, remember 3. 273 when you divide that. So now you have an approximation, which is a low estimate. This is, again, is a lower estimate. Okay. And in the next one, now we're going to use right endpoints with the same figuring. So now we have some of the same function values that we'll use. So we have the summation of f of x, but now f of x times delta x. Now we're using the right-hand endpoints. So right hand, right hand, right hand, right hand. And we have some of the function values. But now remember, we're going to use the 1 where we're not going to use the 0 on this side. We're not going to use the 0. Here we're going to start at the function value of 1/8. So this would be, our first one would be 1/64. If you recall, I put the 0 on the end. It really should have been the first one to consider. So in this one, I'm going to skip the function notation since you already have that, and I think you understand it. So now we're going to do right hand with 8 subintervals. So then we'll start at 1/64. So that is then 1/8 squared. And then the next height would be 1/16, 1/4 squared. So we'd add 1/16. Plus, then the next height would be 3/8. So then we'd have, or the next x value, so we square 3/8 and we get 9/64. Plus, if we square 1/2, we get 1/4. If we square 5/8, we get 25/64, plus, then squaring 3/4 or 6/8, we get 9/16, plus 7/8 squared is 49/64, plus 1 squared, which is 1. And then we multiply that times delta x, which is still 1/8, same as the last problem. So then we add up what's in the rectangle. What's in the rectangle, what's in the parentheses. So multiply that then by 1/8, and you get 0.39, and it would be about 398. So that would be the right-hand estimation for the area under the curve. Now, take the left-hand estimate and then add it to the right-hand estimate, and then divide it by 2 and see what you get. Take that and see what you get. Pause for a second. What do you guys get? So this is about 0.336, very close, right, to 0.3 repeating, which is the actual area. So remember, you're taking an overestimate and an underestimate, so it's combining, and then dividing by 2, you get the average of the two is like really close, okay? So if you recall, we got that 1/3 was the area. So moving on from there, let's take a couple notes now. To find the actual area, we want the number of rectangles first to approach infinity. Before we continue, let's examine summations. So when we're talking about the area, here's a definition. The area A of a region S, that lies under the graph of a continuous function, F, is the limit of the sum of the areas of approximating rectangles. So area under the curve then is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of f of x sub I, remember I is your counter, so that would be the first x value I would use, times delta x sub I. So it's really just adding the multiplication of the height of the function times the base. So then we have the area. This can be rewritten as the following. And if delta x is the same, remember we can factor that out, so we would just get the following. We would get f of x sub 1, because this is the counter, 1, then 2, then 3, then 4, plus f of x sub 2, plus dot, 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 all the way to adding f of x sub n times that whole quantity times delta x. Okay, and if delta x is the same, we'll just write it as delta x. Okay, so consider another approach. Okay, that's just using rectangles. Makes sense? We factor out the delta x. We did that in the last example. So consider another approach using rectangles. Here, area is going to equal this f of x sub I plus f of x sub I plus 1. So there's the first x plus the second x function over 2. Doesn't it look like base 1 plus base 2 over 2? And then it's times delta x. So if you consider, that would be the area of one subinterval, if you will. We put an I over here to be proper. So what we're going to do with the next example is we're going to look at an application by using trapezoids. Suppose the odometer of the car is broken and we want to estimate the distance driven over a 30-second interval. we take the speedometer readings every 5 seconds and record the following table. So you have your table of values as it goes from 0 to 30 seconds. And you notice the velocity is in miles per hour. You lack the agreement of units here because you have seconds in miles per hour. So I'm going to ask that you convert the velocity in the table to feet per second. Why would I do that? If you recall, if I take velocity times time, what do I get? What's velocity times time? Distance. It's distance, right? That's distance. So if the units don't agree on here, if you have velocity in miles per hour and you have time in seconds, you're going to get mile seconds per hour. That's not what you want. You want to have a clear distance. So let's just put these in here. You could multiply by 1.47. That's the approximate multiplication factor to get from miles per hour to feet per second. But we'll go ahead and just put the values in. So 17 miles per hour is 25 feet per second. We'll just fill in 31, 35, 43, 47, 46, and 41. So if I find the approximate distance over the first 5 seconds, I'm going to just put the 2 points here. From the first 5 seconds, here's the point 0.25, and 5, you're at 31. So the area is going to represent the distance. So if I look at this, I have distance. Now notice, this is a trapezoid. So the distance is going to be equal to 25 plus 31, adding the bases, because here's 25, here's 31, and this is a length of 5. So it'll be 25 plus 31 over 2 times 5. So when we calculate this, we get a distance that is equal to, and the units are feet, 140 feet. Okay, and then finding the approximate from 5 to 10 seconds, you might want to pause at this point and figure this out on your own. We start at the point 531 and we go to 1035. Pause now and then open it up to see if you got the right answer or not. And we have the distance traveled. Of course, distance is the area. And so we have distance is equal to 31 plus 35 over 2, the average of the bases, times 5. So with this, you should get a distance that is equal to 165 feet. Okay, at this point, I'm going to pause the video and then I'm going to begin a part 2 video for you. So I will see you. Maybe you're going to listen to the other one later. Maybe you won't, but have a good night. Make sure you listen to it. Bye.